So I guess this is the continuation of designing this, some more things I thought of. So when you're picking your wood for doing things, in this case 6x6 beam, the end profile, the grains, which would be like this part of the wood, the grains, best case scenario is that they are in line with your applied force. This is a best case scenario. Your worst case scenario is where they're perpendicular to your force. So you want it to be parallel, not perpendicular. Don't do that. Terrible idea. Same thing applies anywhere you're using force on wood, including things like axe handles, baseball bats. If you have a baseball bat and you have this in here, make sure when you're hitting the ball, you want your grains, you're going to hit the ball this way so that the force is parallel with the grains and not this way. This is how you break a baseball bat. If you want to look like a boss breaking baseball bats, that's how you do it. So one more on that. So this is what we actually have. If you look at the board, the beam on all three of these, they're all circles. So what do we have there? It's more like we have a pipe inside of a pipe inside of a pipe. So basically we're lifting on consecutive pipes. That's basically what we're doing, with some knot holes in it, which I'm not a fan of. And why is this? Why can't you find a beam, 6x6 beam, that's going to be how we want it, ideally? Well, the reason is they don't let trees grow up like they used to. They're into the quick turnaround on their forest for lumber. So they're not using the biggest trees. So when you get a 6x6 piece of lumber like this, you're not going to get your ideal grain pattern. You're going to get the center of the tree with the round bits shaved off. And that's what we have. So this isn't the best case scenario, and this isn't the worst case scenario. Somewhere in between. And because we have the circles in there, it's like pulling on a pipe instead of, like the curved quarter sawn parts of the grain. So this is actually better, I would say, than the curved quarter sawn pieces. To get a 6x6 beam that is this case, you would have to have a massive tree. Imagine that 6x6. You would need a tree like this big, like 4 to 5 feet across, and you would only get like 2 of those beams out of it, and this would cost way more money. Another thing that I thought of when designing the bottom piece, you might be thinking to yourself, 4 feet across with 8 feet high, that's a little ridiculous. Here's my rule of thumb for this, and it's based on, seeing this in multiple previously engineered, manufactured, and sold things. So L stands for length, X is like x-axis, like you learn in school, and Y is your y-axis. So length of your x-axis, length of your y-axis. So my rule of thumb here is length of your x-axis should be greater than 1/2 of length of your y-axis. Once you go less than 1/2 of the length of your y-axis, it gets a little wobbly and a little scary. This way, your forces, any sway on your load pulls it back and forth. I built a trebuchet before, and you really see it when you're messing around with a trebuchet. Trying to save on some wood down here, and then your trebuchet falls over and the whole thing cracks apart, and you've wasted, a week or 2 of work. Turn it around 90 degrees, looking at it from the front instead of the side, it would look like this. So here we're covered. We have 8-foot rise and 8 feet across, and it's dually supported on both sides. So that's more than our length of X is greater than length of Y. And how are we getting our length of Y here? Because I said we only have a 6-foot beam. How are we getting 8 feet? Well, we have the 6-foot beam rising vertically. And then on top of and below that, each we have a 6x6 beam going perpendicular to that. So they're not perfectly 6 inches, but we're going to calculate for worst case scenario that this is longer than we expect, that they're 6 inches. So 6 inches plus 6 inches is 1 foot horizontal beam thickness total in height on the y-axis. And then we have our wheels in there because that's going to put it up off the ground too. And that is going to give us 0.5 approximately, because they're 5-inch wheels, approximately 6 inches of wheel height off the ground. So total we're at 7.5 feet. Now also you might consider we're pulling, the weight is beneath the beam, so that's gonna change that a little bit in our Y height, but all the force is acting on that beam, so that's where we're gonna make our worst case calculation. That's what this is all about. What is your worst case calculation? Don't find your best case and go off of that one, because one thing goes wrong and the whole thing catastrophically fails. And in cases like a gantry crane where you're lifting heavy weights and you might have to get under it, or you're within the catastrophic failure zone when it happens, it's deadly, and I don't like messing around with that. So we always engineer for worst case. So that concludes this video on extra things that I thought about. Oh no, it doesn't. Talking about this rule, where did I get that from? It's based on observations. From being an artist, you learn shapes of things. So here, distance of the load, 1/2 the distance of the length right there. Got my sawhorses. That height, 1/2 of it. This table saw, here's all your load. There's the height. There's the width. 1/2 of the height. It can be seen in multiple things. Even the step ladder. Step ladder height, width of the step ladder. There's another, the stool. Not quite paying attention to the rule there, but pretty close. So that's why we're going with this. And this is going to be rolling around, so maybe I should go a little bit wider, but I think I'm doing a better job than most manufactured things when I'm doing this. So I think this will be a-okay. So here's a conclusion of this video. Hope you guys learned something else today. Hope you enjoyed this video. Don't forget to like, share, and subscribe. I'm out.